called elevator rides. So there are n people who want to get to the top of a building which has only one elevator. We know the weight of each person and the maximum allowed weight in the elevator. Our goal is to find the minimum number of elevator rides required. So in this example, we have 4 people and the maximum allowed weight is 10. And the optimal answer in this case would be to put 4 and 6 in the first ride, then 8 and 1 in the second ride. That way we will only require 2 rides. So let's head to the drawing board to see how we can solve this problem. So the first thing we can notice is that once we fix the order of the people, then we can calculate the minimum number of rides required in linear time. Here we will start a ride right here, so it will contain 4. We cannot add 8, so we finish the first ride, then it takes 8. We cannot add 6 to it, so we finish the second ride, and 6 and 1 can be combined. So we would require 3 rides in this case. As you can see, it is pretty straightforward to calculate the minimum number of rides required. But we need to find the optimal ordering of the people. So the first naive idea that comes to mind is to iterate over all possible orderings and then for each one calculate the minimum number of rides required, and the answer would be just the minimum of all those. But how many orderings are there? As we know, if we have n elements, then the number of orderings will be n factorial. So the total complexity of our naive approach should be O of n times n factorial. And of course this is too slow for n equal 20. So we need to come up with a faster approach. And to do that, let me show you something. Let's consider this example, and we will fix 1 to be the last element, and we will consider all permutations of the first 3 elements. So we have 3 elements. This generates 6 permutations. So we will have 4, 8, 6, 1. We will also have 4, 6, 8, 1, 6, 4, 8, 1, 6, 8, 4, 1, 8, 4, 6, 1, and finally 8, 6, 4, 1. Now I will go ahead and calculate the number of rides required and the space taken in the last ride up to this position. So here, to get to this position, I would need 1 ride for this, 1 ride for this, and then 1 ride for 6. So I would require 3 rides, and the last ride will have an occupancy of 6. For the second case, I will only have 2 rides, and the last one will have an occupancy of 8. Same thing for this one. For this one, I would require 3 rides, and the last one will have an occupancy of 4. In this case, I would require 2 rides with an occupancy of 10. And finally, for this case, I would require 2 rides with an occupancy of 10 as well. Sorry, this should have been a 4. Now, I want you to notice that we don't need this whole information to calculate how many rides we would require by adding this one. The only information we need is how many rides we've used so far and the total space taken in the last ride. So I know for sure that the answer for this would be 3 with 7 spaces taken in the last ride. For this it would be 2, 9, for this it would be 2, 9, for this it would be 3, 5. This would be 3, 1, because this last ride was full, I cannot add 1 to it, and the same thing for this one, it would be 3, 1. And we actually achieved the optimal answer with these 2 permutations. So what I want you to take away from this is that When adding a new element to some previous elements, we do not actually care about the orderings of the elements. The only information that is important to us is how many writes we required for these previous elements and how much space is taken in the last write. That's the only information we need. So we can use this insight to approach this problem differently. Let's first ask how many subsets exist in a set of size n. And the answer is 2 to the n. This is a pretty well-known fact, and the idea behind it is that you have n elements, and for each one you can either choose to take it or not take it. So you have two choices for each element, so you multiply 2 by itself n times. So basically, if we just iterate over the possible subsets until we reach the full set, then we can bring down our complexity from O of n times n factorial to O of n times 2 to the n. To clarify things further, let's go ahead and work out how this would look like with this example. So let's go ahead and generate all the subsets of this set of 4 elements. So first thing we have is the empty set, then we have singletons. So we have a set containing 4, 8, 6, and 1. Then we have subsets of size 2. So 4, 8, 4, 6, 4, 1, 6, 8, 8, 6, 8, 1, 6, 1. Next we have subsets of size 3, so we have 4, 8, 6, 4, 8, 1, 4, 6, 1, and finally 8, 6, 1. And the final subset is the set itself, so we have 4, 8, 6, and 1. And if you count these subsets, you will actually find 16, which is equal to 2 to the 4th power. Now let's go ahead and calculate the minimum number of writes required for each subset and the space taken in the last write. So if we have an empty subset, we would require at least 1 write, and the space taken in that write is 0. So basically there are 10 spaces remaining. So for the first subset here, 4 by itself, it would require 1 trip, and it will take up a space of 4. This, and for 6 would have this, and finally for 1 we would have 1 and 1. Now it gets interesting. So for a subset 4 and 8, there are two possibilities. Either we process them 4 and 8 or 8 and 4. So the only thing we care about is the last element we processed. So if the last element we processed is 8, this means that we should have come from this element. So at 4 we required 1 write, and the space taken in the last write was 4. So we cannot add 8 to this 4 because it would be larger than 10. Therefore, in this case we would require 2 writes, and the space taken in the last write would be this 8. In the other case, if the last element is 4, then this would depend on this 8 rather. And again, we cannot add this 4 to this 8, but the answer for this case would be 2 and 4 spaces taken in the last write. So the optimal answer would be this, because we will have more room in the last write. So the answer for this would be 2, 4. For this pair 4 and 6, either combination would lead the same result, so for them we would only require 1 write, and it would take all 10 spaces. For 4 and 1 we would only require 1 write, and it takes 5 spaces. For this, It is similar to this case, so the optimal scenario is to leave 6 last, so that way would require 2 rides, and the space on the last strip would be 6. For this we would only require 1 ride with 9 spaces taken, and finally for this we would require 1 ride and 7 spaces taken. Now we can move on to subsets of size 3, and again we ask ourselves what would be the minimum each time we pick one element to be the last one. So if we choose 4 to be the last element, this means that we came from this subset, 8 and 6. And in this case we can actually add the 4 to the 6 and it will still be less than or equal to 10. So the answer, if 4 is the last element, would be 210. The answer, if 8 is the last element, will come from 4, 6. So here we required 1 ride and it took us 10 spaces, so we cannot add 8 to it. So we would require 1 new ride and the last ride will have 8 spaces taken. And if we choose 6 to be the last element, we would have came from this, and again we would get an answer of 210. So the optimal scenario in this case is 28. For the second subset, we have 4, 8, 1. So if we choose 4 to be the last element, that means we came from 1 and 9. So we cannot add 4 to the first ride, so we require 2 rides, and the last one have an occupancy of 4. So if we choose 8 to be the last element, it means we came from here. So we cannot add 8 to this ride, so we would require 2 rides, and the last one will have an occupancy of 8. And finally, if we choose 1 to be the last element, it means we came from here. Then we'll have an occupancy of 2 and a final count of 5. So the optimal answer in this case is 2, 4. And I will leave the rest as an exercise to you. So the optimal answer in this case will be 2, 1. And the optimal answer for the last subset would be 2, 6. Now we reach the final subset, which constitutes the whole set. And the optimal answer for this would be 2 with 9 spaces taken in the last ride, where 8 or 1 are the last elements added. So as you can see here, the number of states we have is only up to 2 to the n, and each state depends on at most n previous states. So this state is the one that depends on the most number of states because it contains 4 elements, so we should consider each element to be the last element. So in this case, it was dependent on these whole 4 states. So that's why the total complexity would be n times 2 to the n. Now you may wonder how we could process these states and these transitions. Basically, how can we store the DP of these states in a concise manner? We cannot just use a DP of a vector or a list. And now it's time to introduce a very important concept when it comes to subsets, and it is the concept of bitmasks. So if you consider 3 elements A, B, C, then we said that the number of all possible subsets will be equal to 2 to the third power, which is equal to 8. Now I invite you to see what happens if we count in binary from 0 to 8 not included. I will represent each number with its binary representation with only 3 bits. So I will count from 1 all the way down to 7. So 0 in binary will be just equal to 0, 0, 0. This is 0, 0, 1, 10, 11, 100, 101, 110, and finally 111. So now if I assign a column to each element I have here, then I can basically read out loud all the possible subsets just from this binary representation. So basically 0 would mean that this element is not chosen in this subset. So here I have 3 zeros, so this should represent the empty set. Here the third element is chosen, so this would represent the subset C. This would represent the subset B. This would represent the subset BC. This A, this AC, this AB, and finally ABC. So what I am getting at is that any subset of a set of n elements can be represented as a binary number of length n. So this means that my DP can be just an array of elements from 0 to 2 to the n. And fun fact, this can be actually computed in this way if you didn't know. This is read 1 shifted by n, 1 shifted to the left by n, and this is equivalent to putting 1 and adding n zeros to it in binary. So basically 1 shifted by 3 would be 1 followed by 3 zeros, which is equal to 8. So we can declare our DP array in this manner. And as we said, each state will be represented by a pair of ints. The first element is the number of writes required, and the second element is the space taken in the last write. One last thing that we should address is that how we transition from some state to all the possible states it came from. So basically, what did we do? We looked over all the elements we had in that subset and we decided to take away that element and see what would be the answer by choosing that element to be the last one. So in this example, if we consider the subset AB, then its bit mask could be 110. So what we can do is to iterate over these bits and check if some bit is set. For example, here the first bit is set, and we can check for a bit if it is set or not by ending this with 1 shifted by the position of that bit. So the position of this bit in this case is 2. So this is just performing a binary AND between 110 and 1 shifted by 2, which is, as we said, equal to 100. So this AND would give us 0, 0, 1, which is greater than 0. So if this value is larger than 0, this means that this bit is set. And if it is set, we need to consider the bit mask it came from. So in this case, we need to consider the bit mask 0, 1, 10. But how we can do that? We can do that by using another binary operation, which is the XOR. So in this case, we will perform the XOR of 110 with 100. And as you know, the XOR of 2 bits is equal to 1 only if the 2 bits are different. So 0 and 0 are the same, so this is 0, this is 1, and this is 0. So just by XORing the bit mask we are considering with all the bits that are set in that bit mask, we can transition to the previous state. And some of you may wonder if iterating through these numbers like this will guarantee that for any given state, all these states it depends on were already calculated when we reach this state. And if you think about it, you can prove that indeed all the states Any given state depends on are calculated before we get to that state. Let's consider again this example of 110. So 110 will depend on two states, namely 0, 10 and 100. And both these states are strictly less than our actual states. And this makes sense because what we do here is that we set some value in our bitmask to be 0. This means we are generating a bitmask that is strictly less than our current bitmask. So just processing the bitmask in order will guarantee that all the dependencies are met. So that's pretty much it. Let's go ahead and check out our code. So we will first start by reading the number of people and the weight limit. Then we will declare a vector of ints to store the weights of the people. We will read the weights. Then I will declare a vector of pair of ints to represent my DP states. The size of it, as we said, will be 1 shifted to the n, which is 2 to the n. And I will initialize these DP values with some large values because I will be minning them each time with their previous states. I will initialize my initial condition, so dp of 0 will be equal to 1, 0. Then I will loop over all possible subsets from 1 to 1 shifted by n. And for each mask, I will loop over all the bits from 0 to n to check if a given bit is on. And as we said, we do that with the AND operator. So if 1 shifted by bit and mask is greater than 0, then we calculate the space taken in the last write, and we can obtain that directly as the second element of the pair. And based on the space taken in the last write, we have to decide if there is still room for the actual person to go on that ride or if it would require a new ride. So if space taken plus the weights of that person is less than or equal to the limit, we're gonna min this state with its previous state, which is mask XORed with 1 shifted by bit. So we take the first element because we're gonna require the same number of rides, and the last ride will be augmented by the weight of that person. And the second case is that if that condition is not met, it means that we would require an additional ride, and on the last ride, the space taken will be just the weight of that person. And in the end, we should just output the answer of the whole set, which will be stored at 1 shifted by n minus 1. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.